Hey, this is Sierra, and I did my presentation on Gibbs free energy, which is a calculation that you use in chemistry. Anything you use, like your phone, car, laptop, the shoes on your feet, makeup, and everything else was made possible because of chemists who reacted things together to make these materials, or even made technology that's constantly creating reactions like a battery. These reactions do not happen on their own. They require minute calculations. One of these is calculating the Gibbs free energy, which tells you if a reaction is going to happen or not. It's the difference between an explosion and a bowl of unreactive material. This idea and equation was created by Josiah Willard Gibbs, who was alive from 1839 to 1903. He was an American mathematical physicist whose work in statistical mechanics laid the basis for a development of physical chemistry as a science. He grew up in Connecticut and later attended and later taught at Yale. To give you a scope of how really well-known and smart this man was, Albert Einstein called him the greatest mind in American history, and many of Einstein's studies actually stemmed from Gibbs' work. Gibbs published a paper in 1873 titled Graphical Methods in the Thermodynamics of Fluids that outlined how his equation could predict the behavior of systems when they are combined. He originally gave it the name available energy in a system, but obviously later they named it after him. To give you a scope of how complex this topic was when he created it, this is a few drawings from his book. The explanation that I'm going to give is a little bit more simple than that. Gibbs free energy tells us about the spontaneity of a reaction, simply meaning will it happen or not. For example, an ice cube melts on its own or a fire burns on its own. You could hypothetically combine any two substances and they have a very tiny chance of reacting with each other if they hit each other at the right time, in the right place, with enough energy. For many combinations, the probability of this happening is so low that we just call them unreactive. So, this is the equation that we're going to use to calculate Gibbs free energy, and the next few slides are going to explain what each of these variables mean. G stands for Gibbs free energy, and then we know that the delta symbol stands for change. For a reaction to have the potential to occur, it must have a negative Gibbs free energy value. This is called an exergonic process. If it has a positive delta G, it is non-spontaneous. We use the other variables found from the reaction to find Gibbs free energy. Enthalpy is what you're most likely already familiar with from your sophomore year chemistry class. Enthalpy change is the heat that is absorbed or released by a reaction at a constant pressure. A negative delta H means that heat flows from a system to its surroundings, and a positive delta H means that heat flows into a system from its surroundings. For a chemical reaction, the enthalpy of reaction is the difference between the products and the reactants. The units of delta H of a reaction are kilojoules per mole. You have to be very careful with this because it is usually given to you in joules per gram, and you're going to have to do the stoichiometry calculations to get it to kilojoules per mole. If a reaction has a positive delta H, it is considered endothermic, and if it has a negative delta H, it is exothermic. Entropy can be simply explained as disorder. For example, a gas is more disordered than a solid or a liquid, with the solid having less entropy than the liquid. If you look at this picture, you can see the one on the left is a solid and the one on the right is a liquid. And entropy is just saying, like, the liquid is a lot more crazy, you might not know exactly where it is, but in a solid, they're kind of staying more still, they're a lot less chaotic. The T obviously stands for temperature of the reaction. It is measured in kelvins, which is a form of Celsius measurement. To convert from Celsius to Kelvin, you add 273.15. So we can look at this equation one more time now that we know what everything is. It Gibbs free energy equals enthalpy minus temperature in kelvins times entropy. Looking at this equation, you really just need to know if the entropy, enthalpy, and delta G are negative or positive, and that's just going to give you what you need. You don't really need to know the exact numerical values. So, if the delta H is negative and the delta S is positive, you're always going to have a negative Gibbs free energy value. So, a negative plus a negative is always going to equal another negative, and delta G is always going to be negative. It's the same way if you look at it inversely, delta G will always be positive. But if delta H is positive and delta S is positive, you're not going to be exactly sure, and that's where you're going to need to look at the values. So I created an example for you guys. Delta H is negative 100 kilojoules per mole. I was being nice, I didn't make y'all do the stoichiometry calculations for that one. Delta S is 757.5, and the temperature is 50 degrees Celsius. So we can just plug those all into the equation, right? There's a catch. We have to convert the Celsius to Kelvin. So if you look right here on this next slide, the enthalpy is negative 100 minus the temperature times the entropy. And we added 273.15 to that 50. And when you calculate it, you're going to get negative 244,128.63 is the Gibbs free energy value. This has a negative value, so this reaction would be spontaneous. And then, here's my works cited. Thank you for watching. Bye.